right, hello. Welcome to the Zero to Hero Develop Your First App with Local LLMs on Windows. My name is Craig Loewen. I'm a product manager at Microsoft. I work on the Windows subsystem for Linux, as well as bringing AI into developer workflows for things like advanced paste and more. And I'm joined today by
Alex. I am a software developer engineer at Microsoft working with partners on the Windows team, helping partners such as yourself to be successful on the Windows platform.
And today we want to take you on a journey of how you can build great AI apps on Windows that all use local workflows. And so if you've never used AI, you're curious about AI, and you want to get started with it for the first time, the session is literally made for you. And I want to start that with a story. I hope this is relatable to you because this is actually my story, which is I wanted to build an AI project. I was really excited to do something that I thought would be cool. And like any developer, I started looking at the frameworks that I would use to do that. I looked at TensorFlow, Keras, PyTorch, Onyx. And then I said, oh, I also need a model. And then I started looking at models, and I looked at convolutional neural networks and other deep Q learning, reinforcement learning, and then that had subtypes of dueling Q networks, et cetera. And all of those models could be used simultaneously across all of those different frameworks, and it became so overwhelming for me that I just moved to a completely different project. I gave up because I said this is too hard. And what we want to do today is take you back to this stage when you said, yes, I want to make an awesome AI project, but it's just a kind of a paradox of choice for me. It's a little too hard to get into this. And what we've done is we've simplified this view for you. We're going to walk you through two examples today using PyTorch and Onyx. And so at the end of today's session, we want you to walk out of here knowing how to make two great local LLM apps. And we're going to show you the A to Z, or A to Z if you're American, of how to do that. The first app is going to be using GitHub. We're going to take GitHub issues, we're going to put them into a local small language model, and it's going to output labels to help us sort, triage, and understand those issues. And we're going to be doing all of that on PyTorch using Phi3. And then we're going to be taking a look at a personal PDF query tool. So it's a tool where you can upload any PDF, and then you can ask it questions in natural language, and it will output answers to you using grounded data of the actual PDF that you uploaded, also in natural language, again running locally using Onyx. And for those of you with really sharp eyes, you've probably noticed that we already talked about LLMs at the beginning of this in the title, and then we're talking about SLMs here when we're talking about the actual projects themselves. And so Alex, what's the deal with that? How do I wrangle the idea of LLMs and SLMs?
Well, one way to look at it is that machine learning models and AI in general they're just programs that use data to make predictions based on a new set of data that you provide to it, right? And an analogy that I like to do is a student. The very first thing that you do when you're a student is you look at a sample, an example of something. The more examples you see, the more different complex equations you can do, the more different things you can understand. So the more parameters a model has literally means the bigger brain of that model, right? And there are different types of AI models. Some models are very specific to language, such as SLMs and LLMs. There are some models that are much more specific to generating an image, right? Models for sentiment analysis, and a bunch of different models that we're going to talk a little bit about here. As well as, of course, classification, which is one of the models that we're going to be using. And specifically, the difference between SLMs and LLMs, you can think of models having these categories of language models, sentiment analysis models, object recognition, labeling. Language models can be split in two big categories, LLMs and SLMs. You've probably heard of LLMs, such as GPT-4, as one example, has 1.7 trillion parameters. And SLMs, such as Phi3, Microsoft Phi3 Mini specifically, has 3.8 billion parameters. So that's 500 times less. It doesn't mean it's 500 times dumber. It's just trained on a different set of data for different tasks that are more specific to be executed on a small machine, not on a large machine that you probably don't have easy access to buy at a store, right? So to give you an example of how you can do that in WSL, Craig is going to do fine-tuning an SLM to label the incoming support issues from the, not terminal, is it terminal?
From VS Code AI Toolkit. We're going to be
No, the repo itself.
the repo itself. We're using PowerToys.
It's PowerToys, not terminal.
Right.
Yeah, that's right.
And so exactly as you mentioned, for SLMs are used for local, and so it's really the same. What we're going to be able to do today is the same as if using like a ChatGPT or Bing Chat online. It's kind of the same purpose, but using it locally, we're able to change the way that it works slightly. We'll jump into how that works. So let me switch to my machine. Let's stay on the demos for now, because actually we have one more slide to go over. Let's talk about the actual scenario. So today, I want to talk about a scenario that I hope is near and dear to your hearts, which is issue triage. Users will label bugs, and then as developers or product managers on the team, we go through and triage them. This is the literal PowerToys repo, which we look at weekly. And, this is the terminal repo, which we look at weekly. And this is what it looks like to label that issue. We go through and label them as what area of the product they are, what level of bug or feature it is. And this helps us plan and prioritize 3 months down the road when we're doing our planning cycle. So for that to actually happen, an engineer has to go read through all of this, understand it, and then apply those labels at the end of the day, right? And those labels are not intuitive if you are not working directly on the terminal team. For example, one of the labels applied on this issue was product con PTY. And unless you know, oh, that means console pseudo teletypewriter, it's just text to you. And it's not something that we would expect everybody to know. In fact, if you asked ChatGPT just off the internet or Bing Chat to understand what that means, it wouldn't know it, because it's domain-specific knowledge that's specific to our use case. And what's great about that is this is a perfect sample case for us to use fine-tuning to train a small language model, or to take an already trained small language model and to teach it about our specific use case. And here's how we're going to do it. The first thing we need to do is do fine-tuning. So we say training at the top. This is already a trained model. We should be talking about fine-tuning. And it's calling into 𝗦𝗲𝗏. And 𝗦𝗏𝗏 is a framework that's used to fine-tune small language models. And that is going to be calling into 𝗬𝗏LoRa, which is a way that we can interface and interact for training and for fine-tuning, training, and interfacing with this model. And then that's calling into 𝗦𝗽3, the small language model, all running on top of PyTorch, running on the Windows subsystem for Linux, running on Windows. So let's recap. Here's the actual steps of what we have to do for the whole process, from this idea of, yeah, it would be great to label our issues with AI, to actually doing it. The first thing is really the hardest, which is I need to pick an AI model and framework. And we've simplified that to you today, because we're just telling you. If you want to have something like ChatGPT to know specific knowledge about your domain, and you want that running locally, we really recommend you try 𝗦𝗽3, and you run that locally on your Windows machine, and see how that works to solve that issue. And then once you've identified, OK, I have my framework, I have my model, we're going to install the dependencies, so WSL and VS Code in this case, and as well as the AI runtime. Then we're going to train the model on our custom data. We're going to fine-tune it with our custom data. And then we're going to run the model in our scenario. So let's switch over to my machine, and we'll take a look at that live. OK, so here I am. And we're going to pretend that this machine is totally new to me. And we're going to install the things we need to run this. There is an awesome tool called WinGet. It is a Windows package manager. And you can literally go WinGet search, and I'm going to type in VS Code in this case. Then you will get access to all that is available on the WinGet catalog. If you used brew or apt-get coming from a Mac or Linux background, it's a very similar user experience. And I can see that there is a Microsoft.Visual Studio Code package here, and it has the moniker VS Code. And so I can do something just as simple as WinGet install VS Code or WinGet install Microsoft.Visual Studio Code. And then this command will install VS Code for me on my machine. And on top of that, this week we announced the ability to install the Windows subsystem for Linux, or WSL, using WinGet. Why did we announce that? That's because we've added additional capabilities to WinGet. If I type in WinGet show Microsoft.wsl, and you can get this by searching for it as well, like I did up here, I can see everything about this package that we've added. And I don't want to paste, thank you. We can see the description, we can see the installer URL, and what I want to draw your attention to is this dependencies option right down here. This dependencies, we've added the ability to depend on Windows features. When you install WSL, you need to enable the WSL optional component as well as the virtual machine platform optional component. Now WinGet can do this for you out of the box, and so you can just type in WinGet install Microsoft.wsl in an elevated command shell or PowerShell prompt. It will install for you. You reboot, run this command again, and you'll be done. So I've installed the base layer of WSL and VS Code. The very last step I need to do is go to extensions, and I'm going to search for AI Toolkit for VS Code. This is how we're going to get the AI runtime. Once you install this, you're going to see this AI Toolkit option on the left side of VS Code, and it's going to do a check for you. It's going to check, do you have WSL installed? Do you have the Ubuntu distro installed? And once you have made sure that you have those things, and it will tell you if you don't, you'll see a model fine-tuning option here. We're going to click that, and you can see that there are options to create a new project. And so I can browse the different small language models that are available for me for fine-tuning purposes. And so I can choose, a project name. I'm going to choose just a sample location, and just to see what this looks like. And I can choose a model. So we're going to choose Phi3. And then when I go configure project, it's actually going to go ahead, build this project for me with sample code. It's going to download the model for me and set up everything that I would need to get started. And the sample that it gives you off the beginning is it shows you a phrase, and then it's asking the AI assistant to determine the tone of the phrase. So like, I ate a delicious croissant, for example, would give you joy. And so that's the sample data that they've given, and that's very easy for you to build. We want to show you today an already set up project of this GitHub issue scenario. So I'm going to flip over to that, which is set up here. Once you've started that, you will get a folder that looks like this. And this is where the magic is. This is your entry point. It's this 𝗦𝗽𝗲𝗀𝗶𝚀. This is how we're going to do our fine tuning. But the actual meat of what's being done is in this 𝗦𝗽𝗲config.json. You can see this is where it's grabbing what kind of fine tuning we're doing. And the most important thing is this text template. You can think of this as the command you would be giving to your small language model of how it's going to interpret your input text and output an actionable result. So we're telling it your job is to label GitHub issues to help teams identify which product and which feature it is, output it as a comma-separated list, don't output anything else. And then we show it, here's the issue info, and then here are the labels that you should be applying. And then where we get this actual data is from this dataset classification.json. So we have this huge, awesome data set of all of the issues we've already triaged. We grabbed that from GitHub, made it into this JSON file, and then we have issue descriptions like, hey, I can't uninstall the previous version to finish the update, and we have the labels that's set up and install for PowerToys.
Very interesting. So it means that this is static data that you downloaded from GitHub to fine-tune your model. This is not dynamic data. You can't run this every time on a service or anything like that. It's a one-time thing that you do with that data set that you collected before, and it does that very last step of getting into the specific things that Phi3 just couldn't know, right?
Exactly. For your student analogy, this would be like the manual I would show to that student and say, learn how to label issues, and then once it's read through all of this, then it knows enough to apply it to some new scenarios.
Super cool.
And so when I go ahead and actually run this, I can go up to this project here, and you're going to run Python fine-tuning invoke olive.py. I've actually already run this. I have a fully trained model present on this machine. And so we're going to flip over to what that looks like in the inference folder of this project. And so I have it open here. There are lots of examples that they already put, like console chat.py, so you can interact with your model. I've just gone ahead and done a little extra work to make this into a Flask website. And let's take a look at how that actually works. So I'm going to hit F5. It's going to start this website up for me. And I've just made a little bit of an interface around using the model so that we can really quickly see what's going on behind the scenes. And this is going to start up, because we're running this in the Windows subsystem for Linux, everything's integrated with Windows, so I get this nice pop-up of, hey, port 5000 is ready in your browser. And I can go ahead and, there we go, load the model. So the first step is I'm going to load the model, and I've set a breakpoint for this. And while it's loading, where we can watch it down there, we're going to take a peek up at what we're actually doing. This is all sample code that was straight from the repo that was created when I did that AI toolkit generate. It copy and pasted it in to just set up the model, our device. We're going to be using our GPU on this machine. And it's all something that I just literally copy and pasted to make this class. And so now that the model is set up, we're going to get a little text here saying that the model is loaded on the computer. We're ready for inferencing. And so let's jump on over to the PowerToys repo. And so here I have an example of an issue, and I'm just going to put in its data as Markdown. And I'm going to copy the rest of this and paste this in. And I'm going to be using the tool Advanced Paste from PowerToys. If you haven't seen this, it's just a cool way that you can paste in different formats. I copied HTML, and I paste directly as Markdown into this. And so now that I have my Markdown data of what the actual issue is, I can hit Calculate Labels. And I set a breakpoint for this, so I haven't yet run. And we're going to see how fast it's able to determine these labels. So I've hit it. It's read the issue, and then now it has fully applied the labels. It was about that fast. And so it's applied the product peak and GitHub repo PowerToys label. And so if we go ahead and actually take a look at this issue, we can see that it is the product peak in PowerToys and on the PowerToys repo. And so in this way, we're able to make an end-to-end scenario of grabbing GitHub issues and then putting them through a fine-tuned small language model and outputting actually actionable results that could help our teams triage faster.
This is super, super cool. And this is all happening locally. You're not even connected to the internet right now, right?
Right. So I am on a local connection, but nothing is leaving the box. It's all running directly in that PyTorch model on my machine.
So for a production scenario, you could actually hook this up with a GitHub hook and actually call your service and do whatever. But it would be running on your box or on your server, not on GPT, on Azure.
Exactly. So yeah, that's our first scenario. And then we're going to jump. Oh, thank you very much. And in that way, we hope that you can try that out. And we want to show you an alternative way that you can also do some of these kind of workflows using a different method on top of Onyx workflows. And Alex is going to be running us through that.
All right. Perfect. So we are going to be using Phi3 for this. And we're going to be building this PDF AI chat app. So first things first, just very quickly, what is Onyx? Why are we using Onyx? Well, first things first, it's a common format for ML models. So whenever you're doing PyTorch, which is what Craig used, you're doing this for your training, right? Whenever you want to ship this to production, we recommend you use Onyx. It can be exported from PyTorch and TensorFlow. It is cross-platform. You can use that exact same model on desktop, IoT, mobile, and the cloud. And it's extremely fast. That's one of the most important things. And in our specific case, we're going to be using DirectML. You don't have to if you don't want to. If you don't run on the CPU, there are models that are specifically tailored for the CPU. And it doesn't support only CUDA. It supports AMD CPUs, GPUs as well, which is the case for that machine and the other one that I have.
And so for DirectML, is that kind of similar to Direct3D, where I don't have to worry about what the hardware configuration is? I just kind of program it for Direct3D, and then the hardware is all figured out. Is DirectML kind of a similar idea?
That's exactly what it is.
Awesome.
And it's going to support NPUs very soon. So you can get exactly the same model, and Windows DirectML is going to choose to run it on the most performant hardware that you have available. And for our specific scenario, we want it to be 100% local. Nothing connected to the internet at all. And In our specific sample, let's say that you have a 1,000-page PDF, right? A very large PDF. There is no way, even if you're running this locally, even if you have the best GPU in the world, you cannot put the whole 1,000-page PDF on the GPU and run a model such as 𝗲𝗃 on top of it. It's just too much data, right? So there is a solution for that, which is called RAG. It's Retrieval Augmented Generation. Instead of sending the whole PDF, 1,000 pages to the GPU, we're going to find the 1 or 2 or 3 pages, depending on how much context you want to provide to the model, based on a separate model, a smaller model, and then we send only that page and the prompt again. So we use the prompt to index and find the right page. It's a very small model. It's only 90 megabytes, the one we're using. There are other options. And then you send that plus the prompt to the LLM, the SLM in this case. So you're pretty much giving a grounding for the model. But this is different from what Craig did, because Craig did pre-training, right? He did fine-tuning, sorry. And fine-tuning is something that you do with static data. This is for dynamic data. You have something that you don't know how your model is going to be used, and you're sending just the specific pages for inference at that specific moment, right? So this can be content coming from the internet. This can be literally anything. So you have your query, your prompt. You send it to the embedding model. You get literally a big array of numbers, literally a multi-dimensional space representation of that prompt, and you preload your PDF. You can chunk it. You can divide your PDF as how well you want it, depending, again, on the specific model that you're using for the embeddings. And you're getting a number for in a multi-dimensional space of what that page represents. So if you do cat and you run that model and you do tiger, it's going to give you a number that is very close because the meaning, it's semantic search, the meaning is very similar. And then we get that result, we get that page and send to the small language model, in our case 𝗲𝗃 mini. And the way that these SLMs and LLMs work is that they predict the next piece of word. Let's just simplify it. It's a token, right? So if you say, tell me a joke, it's going to say KN as one example. It is random. And then tell me a joke, KN. OK, now that I have tell me a joke, KN, it's very likely that the very next token that I should use is OCK. And now that I have tell me a joke, knock. And then it's going to go and go and go. So whenever you see any of these LLMs streaming the results, this is not just a fancy animation that they're trying to do just to impress you. This is literally the data coming from the GPU, coming from these machine learning models, and they're just outputting it to you as fast as possible because you don't want to wait for the whole answer to be outputted just to only then send it back to the user. So recapping real quick our scenario, we want to read the PDF, index every one of the pages. Based on the prompt, we're going to index the search term itself using the same model. Then we literally just do a linear search using Euclidean distance. And then we send that page to 𝗲𝗃 and the original prompt.
So the scenario, just to check my understanding, it would be like if I went and read the whole PDF, I knew where everything was, you asked me a question, I picked out the exact answers, and then I sent that as the prompt.
Yes, you're creating an index, a semantic index. So the very first thing that we want to do is actually do the setup of the machine. Because again, 0 to hero, you don't have anything installed on your box. And for that, we're going to be using WinGet. But I'm going to be doing something a little bit different this time. Instead of running the commands one by one, we're going to be using one command that configures the whole machine with something that is pre-configured. Yesterday, we had a different session that you can look that goes into the details of how that file works. Here I'm just going to show an execution of it. But you can think of it, of WinGet, supporting literally everything that you need for your AI and ML scenarios. It is default on Windows, and it even runs on Windows Server now. And it's equivalent to APT and Homebrew, just like Craig said. You can also do a bunch of different configurations. You can configure developer mode. You can configure dark mode. You can literally install extensions on VS and VS Code. You can literally do pretty much anything that you as a developer would do in your box whenever you're setting it up. So this is an example of execution. This is open source. You can check it out. It's on my GitHub. And I'm doing a check of the OS version. I'm creating a dev drive. I'm enabling developer mode. I'm turning file extensions on Explorer. I'm installing a bunch of different packages, VS Code, fuvs. Then it's just checking for everything. Then I press yes. Are you sure you want to do this? Yes, I'm sure. Go ahead. Then you go get some coffee, come back, and it's done. That's pretty much it.
And so we showed kind of like an a la carte model at the beginning of you can use WinGet to grab specific stuff, or in our case, we have a fully set up project. We've created a definition of what you need to use this project. That's just one file, and it's just as easy as running WinGet configure, which can apply that whole thing for you.
Yeah, so every time that I open up a new box, I run that command and it just set up everything. I don't have to remember, oh, which software did I use once? No, every time that I set up a new machine, that's what I do. And whenever there's some new version or a new interesting software that I want set up every time, I just edit that file. It's on Git, it's just YAML. So, okay, now that our machine is completely set up, let's actually download models. Because now that we know what a model is, where do we actually get them? I don't want to get into the trouble that Craig did of fine-tuning a model. I want to get something done. I want literally to have a catalog and pick the best machine learning for X, Y, and Z. And you can use Hugging Face for that. Hugging Face is a community website, pretty much a huge repository with pre-trained machine learning models. It has pretty much anything that you would like. It has Stability AI Stable Diffusion for image generation. It has OpenAI's Whisper, which is a very tiny model for speech recognition. And of course, Microsoft's Phi-3 for advanced language understanding and generation. They're completely ready to use. Most of them has Onyx version, so you can literally just download it. And let's actually go for a quick demo. If we switch to number 4. All right. So as you can see, this is huggingface.co. If we click here on models, you see that we have a little bit over 500,000 of them. So that's something for us to start, right? I think that's enough. And on the left side, you can filter out by different types. And what I'm going to choose is sentence similarity. This is what's going to generate our semantic index. This is what's generating the embeddings. And I'm literally just going to pick this first one, which is the most used one. This one in particular didn't have an Onyx version. I found a fork. You should not be putting models in your Git repositories, right? Because these are huge files and you probably don't want to version them. Let's say you have one version that is 2 gigabytes and you update it to a new version, your Git's going to get into 4 gigs. You probably don't want to do that. But Hugging Face is a Git repository only with the model. So you can clone this. You're literally going to have everything. So this one, it's a fork that has the specific Onyx version. And all I need for this, from this one is the model.onyx, which is this 90 megabytes file, and the vocab.txt. Again, remember, models work with numbers, not with text. So you need a table, pretty much, that translates the token, KN for knock, to index number 123. And the model itself, it works with the number 123, not with the word KN.
And so
that's what the vocab does.
And I'm able to just download it directly from this files place, or I could clone this whole repository and put it on my.
Yes. This one in particular, you're not going to get much by downloading them manually. They're just 2 files. That's all you need. If you're downloading Phi, we have multiple different versions of Phi. Hugging Face have a CLI, so you can use the CLI to filter out. I only want the DirectML version optimized with AWQ, whatever. But you can just clone the whole thing if you want to. So I'm literally just downloading those files for this first model. And for Phi-3, for Microsoft's Phi-3, I just went to the website, search for Microsoft, and there's Phi-3 Mini 4K. That's the window of how many tokens it remembers. It's pretty much how much it can remember already in the Onyx version. And if you go to Files and Versions, you can download the specific version. I'm going to download the DirectML version. That's the AWK block 128. You don't have to understand how that works. But in this case, for this model, we need all the files. And after you download it, you put it in your project. So that's literally what I'm doing. I have the All-Mini 1 version here, and I have the CPU version just in case something goes south. I have my backup. But things are working. And if we go quickly back to the slides. OK, so that's how you download a model from Hugging Face. Now, let me actually show you some code back at this machine number 3. All right. So here, first things first, let me show you the code running. This is my RAG sample. Let me actually debug it. So you can see that I'm not doing anything magical. This is real code. And whenever I click on the index PDF button, I'm prompt to select a PDF file. In this case, I'm downloading all the Windows documentation for AI. This, if I'm not mistaken, this is a 40 megabyte PDF, around 1,300 pages. So there's no way that you can index and infer on the whole content all the time. And whenever I double click on it, it starts reading the PDF and it's indexing it, right? So I'm literally getting page by page and running it to the GPU. I'm not sending one by one. I think I'm sending 32 at a time because it's faster. I have enough GPU power to do that. But you can see that in about 10, 15 seconds, it indexed the whole PDF. And now I can ask something about it.
So is that like indexing is the equivalent of reading all of that and then understanding this has this piece of information here, this is here, this is here?
Yes, that's exactly what it is. And what we've done is for every one of those pages, we get one of these very big vectors.
Cool.
Right? So we can ask it something. What do you want to ask?
Let's ask it something pretty specific, like what do I need to run text recognition APIs?
OK.
For example.
Let's see. What do I need to run text recognition APIs? And if we click on the answer button, this instantly found page 17 and page 26. And it's running a little bit slower than usual. This is probably because it's offloading to my shared GPU. But usually this goes like very, very, very fast. To run text recognition APIs, you need the WinApp SDK specifically version 1.6 or later. That's correct. Experimental 1, I think, has that support, as it includes the new artificial intelligence text recognition APIs. And it goes on and on. But it used the exact page. And let's see if these pages are actually right. Let's click here on the show page. This is actually quite small for us to read, but get started using AI-backed APIs in your app. This looks right.
And I see text recognition with OCR right there. So it is grabbing the actual grounded data of, AI models can make mistakes. We're making it as hard as possible for it to make those mistakes by feeding it the direct data from the applicable text.
Yeah. And it does have another page here that it it did send to the model, but I don't think it used anything specifically from here. But that's literally how it works. We can ask anything about this PDF, and it's going to be able to infer something based on that grounding data that we're sending. And how are we actually doing this? Let me close the app real quick. Whenever I click on the index PDF button, the first thing I do, of course, is read the PDF. I'm just using a third-party library here to read the PDF contents and removing a few characters that are not important for me. After that, I split it in 512 characters. That's roughly the size that this specific model accepts as its input, because if you send anything more than that, it truncates it. And I don't want it to do that. I want to index all the content.
And when you grab that model specifically from Hugging Face, that data is available on that repository itself. It shows you how to get some of these values in sample code. So if you grabbed other models, you would be able to see some of this information there.
Yes. Every single model on Hugging Face has an example of how to use it. Sometimes you need some magical numbers, like what's the size of the vector that I return, or what are the expected inputs of my model. All of this information is on Hugging Face, and there are other tools available, of course, to help you out with that. So now that we have split the content and made sure that it's to the right size, this is just progress, not important, then we call our RAG service that initializes with all that content. And this method internally is just making sure that the model is initialized, and it's sending, in this case, 32 blocks, not 64, 32 blocks at a time to my get embeddings async, which is the method that actually calls the GPU, the DirectML functions. So here I'm actually calling and initializing the tokenizer based on that vocab text file. Then I tokenize, I convert that string to numbers, to an array of numbers. This is just a creation of the inputs. This is, again, based on Hugging Face. Again, all this code is open source, so you can check it out, clone it, test it on your box. And then I'm actually creating the output tensors. This is the 384. That's the magic number that I mentioned that you can get from Hugging Face website. It's just a magic number. It's this particular model returns an array of 384 floats that represent that input, that text that you send to the model. This is literally the size of the output. And here I'm actually running it and getting the results. And of course, splitting it back, because I'm setting 32 at a time, I'm splitting it back to return 32 things. It returns one big, in this case, 32 times 384 array. And this is all that's needed to actually do the indexing of the PDF. When I click on the next button, the Ask SLM, and I type something, I'm generating a prompt 253. And this specific format, you've probably seen like this system and user and assistant. You don't have to know this. This is, again, in Hugging Face on all the documentation that you can find. This is just the expected way that the model was trained on. So it's what it expects for you to send your prompts. You just have to form it in that particular way. So I'm just saying you're a helpful assistant. You should answer questions about this information in a direct and simple way using only this content. And then I'm doing a RAG service search. This method is getting the embeddings for that one term. It's only one. I'm sending once again with the exact same model, getting 384 floats for that one, and returning it back to, with the contents, with the actual pages. Then I just format that in a big string that I'm sending 253. Then I'm sending all the contents of those pages 253. Just splitting and grouping things properly and saying, hey, assistant, now is your turn. Give me the answer.
So this is the code that's actually preparing the prompt, like a literal prompt that we would be sending, and it's injecting that relevant, those pages that we saw earlier.
Yes, that's the RAG process.
Very cool.
And then whenever I click on whenever I call this method in for streaming async, I'm actually tokenizing the input of that whole prompt to the model. 253. I'm just initializing a few things to count some times. Then I have the actual code that is generating the next token, getting that information back from the model, and I'm decoding that back. Because again, the model is returning me a number. I'm getting the tokenizer to transform that number back to KN, specifically for the knock knock joke. I'm just waiting for a few things to happen. Maybe they happen, and then I just output that to the screen. That is all the code that you need. It's not a lot of code. So it's very simply, you can leverage these models locally without having to understand how all the fine-tuning works. You can just go to Hugging Face, download the model, run it locally. And the exact same model can run on different workloads because of the Onyx runtime, right? All right. So that is pretty much it. We've done everything that we were set to do, right?
Right. So we showed you two different ways that you can use local models. In the first example, AI Toolkit is a great way that you can just get started immediately and grab and fine-tune based on your custom data. And what's great about that is you'll notice that the context window that we were sending was just the context of the issue itself. The model was fine-tuned on our data, so it can be pretty snappy when responding back. And then we also took a look at another way to do a similar application using RAG, where we're able to index on a very large data set that is dynamic, grab the pertinent pieces of information, and then show exactly that to the model to ground and make sure that any of its response that's coming back is accurate based on that knowledge. And so we also showed you about how easy it is to get set up with the A to Z part of that, of setting that up using WinGet. And all of the code, again, is available online. And we have some learn more resources for you. Some of these have already happened, so we encourage you to check out the stream of them. But they are ways that you can get deeper into your AI journey. They are applications like using DirectML, using AI for real things, and bring AI experiences to your Windows devices. We also recommend that you check out 𝗦𝗲𝘀𝗀. 𝗦𝗲𝗀 is a third-party tool that can allow you to download small language models onto your machine really easily. And they can be a great way to explore different models. I know we used Phi-3 in both of our examples, but there are other language models out there like Llama 3, et cetera. And you can play around with how these different models behave on some of your different scenarios quite easily. And last but not least, the bottom 2 links there show the links that you can get all of this source code online. So thank you very much for tuning in. We'll open the floor if there are any questions, and thank you and have a great build.